Let's now move on to the study of the prime implicant selection phase in the case of multiple functions. First, we need to analyze how the presence of multiple functions and the potential sharing of implicants affect the cost evaluation, which we have so far computed based on one of the two commonly used figures of merit, the cardinality and the number of literals. As for cardinality, we know that each implicant corresponds to an AND gate, and each function corresponds to an OR gate. Therefore, the total number of gates with a generic number of inputs in the circuit is equal to the number of selected implicants, excluding those composed of a single literal, plus the number of outputs. Here's an example. In the first expression, we have two implicants, excluding shared ones which will be counted later, one of which consists of a single literal. In the second expression, we have one additional implicant. And finally, there are two shared implicants. In conclusion, the total number of implicants is 5. If we subtract 1 for the single literal implicant and add 2 for the number of outputs, we get a final number of gates of 6, as we can check in the schematic shown on the left. Let us now analyze the second figure of merit. When selected for the first time, an implicant consisting of n literals needs n-1, 2 input AND gates, and 1 2-input OR gate. If the implicant is selected again for another function, and therefore it is shared, it requires only 1 2-input OR gate. Finally, the last implicant selected for a function does not require an additional OR gate, since it can use the second input of the previously instantiated OR gate. Taking all these factors into account, similarly to how we handled this metric in the single output case, we can conclude that the total number of 2-input gates in the circuit is equal to the total number of literals minus the number of shared implicants minus the number of outputs. Here's an example. The first equation contains 5 literals, the second contains 4, and the last two contain 3 each. This gives a total cost of 15 literals. We then subtract 2, that is the number of shared implicants, and 2 for the number of outputs, resulting in a total number of 2-input gates of 11. In the schematic on the left, each n-input gate is annotated with the number of equivalent 2-input gates it represents. Adding all those contributions gives us a total of 11, which confirms our calculation. Let us now move on to the construction of the prime implicant chart. This table is built by aligning the minterms of all functions side by side as columns, with a vertical line separating the columns of one function from those of the next. We will fill the table using x's, just as we did in the single function case, but now we must take into account the function coverage mask associated with each implicant. In particular, for each implicant, we place an x only under the minterms of the functions corresponding to the positions of ones in its mask. Here is an example. These are the prime implicants obtained during the prime implicant generation phase, and this is the subsequent prime implicant chart. To better understand how to interpret the masks, consider implicant P3. It covers minterms 1 and 5, but only for function g. So even though function f also includes minterm 5, we do not place an x in the corresponding position for f because the implicant does not apply to that function according to its mask. We complete the table by adding the cost column based on the chosen figure of merit. The only difference compared to the single function case is that, when using cardinality as the cost function, the cost column is no longer optional, but it is fundamental for executing the prime implicant selection phase. Here is the cost column for the current example when cardinality is used. And here is the corresponding cost column when using the number of literals as the metric gate. The solving strategy is exactly the same as the one studied in previous lessons. We apply essentiality and dominance criteria iteratively, and, if the table is cyclic, we eventually execute the branch and bound algorithm. However, in the case of multi-output synthesis, a few additional considerations must be taken into account. In particular, the fact that the selection of an implicant must be evaluated independently for each function. The identification of an essential prime implicant is performed individually for each function. An implicant is considered essential for a given function if there is a column with only one x corresponding to at least one of its minterms. Once an essential prime implicant is identified, we remove all columns of that function where the implicant has an x. We add the implicant only to the cover set of the corresponding function, and we eliminate any row that no longer contains an x for all the functions. Let's continue the example using the number of literals as the cost metric. P5 is essential for G, since it is the only implicant that covers minterm 13. We then remove all covered columns for function G. This gives us the updated table. In this case, there are no rows to remove. Finally, we add P5 to the cover set of G. Only when an implicant is selected for the first time, its cost must be updated. This cost update accounts for the potential sharing of that implicant across multiple functions. Specifically, choosing an implicant for the first time means that we pay the cost of implementing it, in particular, the ungate. If the same implicant is selected again for another function, that implementation cost no longer applies. In the case of cardinality, the cost changes from 1 to 0, because selecting the implicant again does not require adding any more AND gates to the circuit. In the case of the number of literals, the cost is updated from the number of literals to 1, since selecting the implicant again will only require one additional 2-input OR gate. Let's go back to the example where we selected implicant P5. If the cost function is cardinality, its cost changes from 1 to 0. If the cost function is the number of literals, its cost changes from 3 to 1. Row dominance is applied by considering all functions together. An implicant Pi dominates another implicant Pj when Pi covers for every function, at least all the minterms covered by Pj, and Pi has a cost less than or equal to that of Pj. As in the case of a single function, the row corresponding to the dominated implicant is removed. This simplification can sometimes result in the emergence of secondary essential prime implicants, which should be handled as previously shown. Let's go back to our example from the beginning to illustrate an interesting scenario. Implicant P5 dominates P4 because P4 covers a subset of the minterms covered by P5, and both have the same cost. This results in the elimination of P4 with no changes to the current cover set. Unlike row dominance, column dominance applies only within a single function. It follows the same rules used in the synthesis of a single output function, and it leads to the elimination of the dominated column. Let's restart the example from the beginning once more. We can observe that minterm 2 dominates minterm 0 for function f. Therefore, minterm 0 is eliminated with no changes to the current cover set. We apply the three criteria iteratively, as discussed, until we reach either an empty table or a cyclic one. In this example, I highlight all the X entries that lead to the identification of an essential prime implicant. These implicants are P1 and P6 for function f, and P3 and P5 for function g. We select them and eliminate nearly all columns, and consequently all rows as well. This leads us to the final solution, where I show the complete covering, the resulting expressions, and specifically in this case, we observe that no implicants are shared between the functions. The final cost is also displayed. In the case of a cyclic table, as we've learned, we must adopt a pseudo-exhaustive search strategy such as the branch and bound method. This method must be applied with the following considerations. At each branch, a decision must be made for a single function only. Therefore, we must define a systematic order not only for selecting the implicants, as we did in the single function case, but also for selecting which function to cover at each step. For instance, one could explore the solution space by covering one function at a time, or alternatively, by alternating decisions between the different functions. Finally, the selection of an implicant is made per function, meaning the same implicant can be selected multiple times, once per function, during the exploration. Here's an example of a cyclic table of a problem considering the cardinality as cost function. On the right, we see the corresponding branch and bound tree. We first select P0 for F1, yielding a cost of 1. Then, we select P0 again for F2, which does not increase the cost under the cardinality metric. Next, we select P2 for F1, increasing the cost by 1. And so on, alternating selections between F1 and F2. In conclusion, the algorithm for the prime implicant selection phase is as follows. First, we construct the prime implicant chart. Once the table is ready, we apply the essentiality criterion to identify essential elements. Next, we apply the row dominance criterion, followed by the column dominance criterion, to further simplify the table. After applying these criteria, we check whether they have modified the table. If they have, we repeat the process starting from the essentiality criterion. If not, we move to the next step. Then, we check if the table is empty. If it is, the algorithm ends. If not, we proceed to execute a search algorithm, such as branch and bound, to complete the covering solution.